Good morning, dear students. Remain safe and sound and follow the safety guidelines provided by Department of Health of our country due to the current problem of COVID-19. Dear students, you placed your problems in the topic functions. So just for the sake of your reference, I prepared this video for you people in order to explain that topic. So let us look at this topic. In this video, I'm going to explain the concepts of the types of functions with the help of examples. In the unit 1, in the subject of mathematics, you people have to study relations and functions. Relations and functions, this topic is divided into three number of subtopics. One is relations, secondly functions, and third inverse trigonometric functions. So I think this one and this one are your problematic areas. In functions, we can see the three number of subtopics. One is types of functions, secondly composition of functions, and third invertible functions and its inverse. Now, there are number of classifications of functions. In one classification, it is divided into two parts, algebraic and non-algebraic functions. In next classification, it is divided into again two parts. One is many-one function and secondly one-one function. In the third classification, function is divided into three parts. One is injective function, secondly surjective function, and third bijective function. In the fourth classification, it is divided into again two parts. One is implicit functions, secondly explicit functions. In the fifth classification, it is again divided into two parts. One is continuity and non-continuity of the functions, or we can say discontinuity of the functions. And in second part, it is again divided into two subparts, which is differentiability and non-differentiability of the functions. Now, let us see that what the types of algebraic functions you people have already studied at class 11th. Those were modulus or absolute functions, constant functions, linear functions, quadratic functions, cubic functions, biquadratic functions, polynomial functions, reciprocal functions, square root functions, greatest and the least integral functions, rational functions, discrete or split up or piecewise functions, etc. These things you people have already studied at class 11th. In non-algebraic functions, you people studied about trigonometric functions. About inverse trigonometric functions, you will study in this separate chapter. Logarithmic functions, exponential functions, hyperbolic functions, you will study in higher classes. Now, again, injective functions, which is also known as one-one functions, it is divided into two parts. One is one-one onto into function. Secondly, one-one onto functions, which is also known as bijective functions. Again, surjective functions, which are also known as onto functions, it is divided into two parts. One is many-one onto functions. Secondly, one-one onto functions, which is also known as bijective functions. We will see about bijective functions. Then this is actually injective or one-one function plus surjective or onto functions. Means if a function which will be both injective and surjective or one-one and onto, then that function must be bijective function. And if we will have a bijective function, then that type of functions are called invertible functions because we can find out the inverse of such functions. Now, again, there is another classification of the function what I have already mentioned before. It has two parts, which is many-one function, which is also known as non-injective functions. Second part is one-one or injective function. Now, many-one function, it is again divided into two parts. One is many-one into function, secondly many-one onto functions. 1 or injective function, it is also divided into two subparts. One is 1 into function, and secondly 1 onto functions, which is also known as bijective functions. Now, what is injective function or 1 function? So its definition is already formally explained in the definition mentioned in the study material, what we have already provided to you people. Okay, but even for the sake of your reference, I want to tell you that those functions are called injective or 1 functions, in which every member of the range of the function is uniquely associated with the members of the domain of the function. Again, I repeat, those functions are called injective or 1 functions, in which every member of the range of the function is uniquely associated with the member of the domain of the function. Now, here I have explained this thing with the help of some examples. Example number 1. Suppose if we have a function f defined from a to b, defined as fx is equal to x plus 1, where a is equal to the set containing elements 1, 2, 3, b is the set containing the elements 1, 2, 3, and 4. Then, under this definition of the function, this diagram we can obtain, which is also known as mapping diagram. Now, here f as a relation, we are getting its members in ordered pair as 1, 2, 2, 3, 3, 4. What it is very clear from this diagram. Now, clearly, here domain of the function f is equal to a is equal to the set containing elements 1, 2, 3. Range of the function f, that is equal to the set containing elements 2, 3, and 4. And this is clearly the subset of the set containing elements 1, 2, 3, 4. And this set is the codomain of the function f. And the codomain of the function f is the set B. Here we are observing that number of elements of the set A is less than that of the number of elements of the set B. Now, since here range of the function f, this is the subset of the codomain of the function f, therefore this function is 1 into function. Now see here the example number 2. If we have a function f defined from a to b, defined as fx is equal to x plus 1, where a is equal to the set containing elements 1, 2, 3, b is equal to the set containing elements 2, 3, 4, then this will be the mapping diagram. Now here we are observing that number of elements of the set A is equal to the number of elements of the set B. F as a relation has the members of ordered pairs as 1, 2, 2, 3, and 3, 4. Clearly, here domain of f is equal to the set A is equal to the set containing the elements 1, 2, and 3. Now here, range of the function f is equal to the set containing elements 2, 3, and 4. And this is equal to b, which is the codomain of the function f. So since we are observing that in this example, range of the function f is equal to codomain of the function f, therefore the function f from a to b is 1 onto function. Example number 3. Suppose we have a function f defined from r to r, defined as fx is equal to x plus 1, where r is equal to the set containing x such that x is a real number, which is obviously an infinite set. Now, here we cannot investigate the injectivity of the function just like we did in these two examples by drawing here the mapping diagram. Why? It is so because that here domains were finite, but here domain is not finite. It is in fact infinite. So here there is the abstract method of the investigation about the injectivity of this function over the domain of this function, which is actually an infinite set. So here NB stands for to remember that for the function f from a to b, where both the sets a and b are the subsets of the set of real numbers, because at the class 12th we have to study about real valued functions or real functions. So that's why whatever the domain and range will consider, those will always be the subset of the set of real numbers. So here we are going to consider one function f defined from a to b, where both a and b are the subsets of the set R. if x1 and x2 are belonging to capital A such that fx1 is equal to fx2 implies and implied by x1 is equal to x2 for all x1 x2 belonging to capital A, then f from A to B is an injective function. Means if this result will hold in context of any function whose domain is infinite, then we can say that the function is an injective function. Or even we can observe if this condition, then also we can say that the function is injective function. So under this condition, suppose if we will have a function f from A to B where A and B are the subsets of capital R, if x1 x2 belonging to capital A such that x1 not equal to x2 implies and implied by fx1 is not equal to fx2 for all x1 x2 belonging to capital A, then f from A to B is an injective function. So here actually both of these two conditions are equivalent to each other. Both of them are same, but it is the affirmative statement and this is negative statement. Here both of them are equivalent to each other. If any one of these two will hold, we can say that the function is injective. Otherwise it is many one function which is not injective function. So let us see the process under which we can verify that whether this function fx is equal to x plus 1 over the set of real numbers is injective or not. Now let us assume that x1 and x2 are any two elements of the set R which is the domain of this function such that fx1 is equal to fx2. Then since fx is equal to x plus 1, so that's why fx1 will be equal to x1 plus 1 and fx2 is equal to x2 plus 2. Here this one and this one will be cancelled so that we can obtain x1 is equal to x2 for all x1 x2 belonging to capital R which is the domain of the function. So therefore f from R to R is an injective function or 1 function. Now example number 4. Suppose we have a function f defined from capital R minus singleton carrying 0 to capital R where R is the set of real numbers defined as fx is equal to 1 by x. Here we are going to take reciprocal function. So we have to investigate that whether it is injective function or not. For that, randomly or arbitrarily, we are going to take two number of elements of the set R minus singleton carrying 0 such that fx1 is equal to fx2. Then according to definition of the function, we will have 1 by x1 is equal to 1 by x2 and this will imply x1 is equal to x2 for all x1 x2 belonging to capital R minus singleton carrying 0. Here actually this is the set of all non-zero real numbers. We know well that our reciprocal function is undefined at x is equal to 0. So that's why this 0 is exempted from this set so that we are getting here the set of all non-zero real numbers. So clearly this explanation is showing that the function f from R minus singleton carrying 0 to R is an injective function. Example number 5. Suppose we have a function f defined from R to R, define fx is equal to greatest integral function of x plus 1. Now, in this case, even we can consider some examples by which we can show that whether this function is injective or not. Here, we are observing that if x is equal to 1.3, which is obviously a member of the set of real numbers, for which f of 1.3 is equal to greatest integral function of 1.3 plus 1 and this is equal to greatest integral function of 2.3 and obviously it is equal to 2. Again, it will take another real number 1.2 for which the value of f of 1.2 will be equal to greatest integral function of 1.2 plus 1. This is equal to greatest integral function of 2.2 and its value will again be equal to 2. So we are observing what? That the images of the real number 1.3 and 1.2 both of them are equal to each other. But 1.3 and 1.2 both of them are not equal to each other. So if for any two members, two or more than two number of members in the domain of a function, there is single image in the codomain of the function, then that type of function will not be considered as an injective function. That type of function will be called many-one function. So by presenting some counterexample also, we can show here that the given function is not an injective function or a many-one function. Now consider example number 6. In this example, we have a function f defined from R to R. Define fx is equal to sin x. For this function, we are observing that if x is equal to pi by 4 radian, then f of pi by 4 radian is equal to sin pi by 4 is equal to 1 by square root 2. Again, it will take x is equal to pi minus pi by 4, which is actually thrice pi by 4. Then f of thrice pi by 4 is equal to f of pi minus pi by 4 is equal to sin pi minus pi by 4 radian. And we know well that sin pi minus theta is equal to sin theta. So we will have here sin pi by 4, and this is equal to 1 by square root 2. So even in this case, we are observing what? That the images of thrice pi by 4 and pi by 4 are equal to each other, but thrice pi by 4 and pi by 4 are not equal to each other. Means f of thrice pi by 4 equal to f of pi by 4 doesn't imply that thrice pi by 4 is equal to pi by 4. So even this calculation is showing that the function fx is equal to sin x is not an injective function, so that it is many-one function. Now consider another type of function, that is surjective or onto functions. Regarding surjective or onto functions, precisely I want to discuss here the definition, and in detail the definition of this function or this type of function is mentioned in the study material. For the sake of your reference, I am telling you that those functions are called onto functions or injective functions, in which we can obtain the pre-image of every element of the codomain of the function in the domain of the function. Again, I repeat, those functions are called subjective or onto function, in which we can observe that every element of the codomain of the function is associated with the elements of the domain of the function. If this thing will happen, then that type of function will be called as onto function or surjective function. Now let us consider example. Suppose we have a function f from a to b defined as fx is equal to x plus 1, where a is equal to the set containing elements 1, 2, 3, b is equal to the set containing elements 2, 3, 4. So here, according to this mapping diagram, we are observing that every element of the codomain of the function b, it is associated with the elements in the domain of the function. So since every element of the codomain of the function is associated with the members of the domain of the function therefore this function must be an onto function or surjective function. As a relation, this f will have the elements in ordered pair as 1, 2, 2, 3 and 3, 4. Range of the function f is 2, 3, 4, and this is equal to codomain B. So since we are getting that codomain of the function f is equal to range of the function f, therefore we can say that the function f from a to b is surjective function. One more way we can define the surjectivity of a function, and that is what, according to this example, that if codomain of a function is equal to range of the function, then that function must be considered as a surjective function or onto function. So here we are getting the same. Here codomain of the function f is equal to the range of the function f. That's why this is the example of a surjective function. Now consider example 2. In this example, we are going to take one function f from a to b defined fx is equal to x plus 1, where a is equal to the set containing elements 1, 2 and 3. B is a set containing elements 1, 2, 3 and 4. So according to mapping diagram, we are observing what? That we are getting the association of every element of the codomain of the function except the element 1. So since we are getting that there is at least one element in the codomain of the function which is not associated with any element in the domain of the function. Sorry. So that's why that type of function cannot be considered as a surjective function. We can see here the range of the function f is equal to 2, 3, 4, which is the proper subset of the codomain containing elements 1, 2, 3 and 4. Here codomain of the function is B. So since we are getting that range of f is the proper subset of the codomain of f, that is range of f is not equal to codomain of f, therefore the function f from A to B is not onto or surjective function. Example 3. Suppose we have a function f defined from A to B, define fx is equal to x square, where the set A is equal to the set containing elements minus 2, minus 1, 0, 1 and 2, and B is the set containing elements 0, 1 and 4. So here this is the mapping diagram where we are observing that more than one elements in this set A have the same image in the set B. Here minus 2 and 2 have the image 4, minus 1 and 1 have the image 1, and 0 has the image 0. Therefore, f as a relation will have the elements as ordered pairs minus 2, 4, minus 1, 1, 0, 0, 1, 1, 2, 4. So here we are observing that f of minus 2 is equal to 4 is equal to f2, f of minus 1 is equal to 1 is equal to f1, and so on. So obviously, since many of the elements of the domain of the function, more than one element of the domain of the function is associated with some element in the codomain of the function, so that's why this is not injective function. This is one thing. Secondly, we are observing that range of the function f is equal to the set containing 0, 1, 4, and it is equal to codomain of the function f. Therefore, f is surjective or onto function. Now, consider example 4. Suppose there is a function f from A to B defined as fx is equal to x cube, where A is equal to 1, the set containing elements 1, omega and omega square. B is equal to the set containing elements minus 1, 0 and 1. Here 1, omega and omega square are nothing but the cube roots of unity. You know well that the value of omega is equal to minus 1 plus iota square root 3 by 2, and omega square is equal to minus 1 minus iota square root 3 divided by 2, where iota is equal to under square root of minus 1. So here, according to my mapping diagram, we can observe that 1 omega and omega square in the domain of the function are uniquely associated with the element 1 of the codomain B of the function. So function f as a relation will have the elements in the form of ordered pairs as 1, 1, omega square, comma 1. So range of the function is the singleton carrying 1, and it is the proper subset of the codomain of the function. So that's why here this function is not surjective function, or it is not onto function, so that we can say that it is into function. Those functions which are not onto are called into function. And also we can say that this function is not injective. It is so because that more than one elements in the domain of the function, there is single image in the codomain of the function. So that's why we can say that it is not an injective function. Consider example 5. Suppose there is a function f defined from R to R. Define fx is equal to x plus 1, where R is equal to the set of real numbers. Now, in the previous cases, we observed that if we will have finite domain, then merely by analyzing mapping diagram, we can say that whether that function is surjective or not. But if we will have infinite domain, then how we will be able to decide that whether given function is surjective or not? For that, here there is one rule. You can understand it properly. Here that rule is that if a function f from A to B is onto, then for all y belonging to capital B, there exists, this is a symbol of there exists, at least one x belonging to capital A such that y is equal to fx. Again, I repeat, it is very abstract concept. F a function f from a to b is onto or surjective if, this stands for if and only if, for all y belonging to capital B, which is the codomain of the function, there exists at least one x belonging to capital A such that y is equal to fx. In another way, we can say that if range of f is equal to codomain of f is equal to b, then we can say that the function f from a to b must be onto or surjective function. Now see about the verification that this function is surjective or not. Let us assume that y is an arbitrary element of the set R, which is actually here the codomain of the function, such that y is equal to fx for some x belonging to capital R. Here it is remarkable that this R is actually the domain of the function fx. Then as per the definition of fx, we will have y is equal to x plus 1, then x is equal to y minus 1. Now we are observing that this y minus 1 is always a real number for all real values of R, all real values of y. This expression will always be a real number if y will be a real number. So there is not a single real number y for which y minus 1 may not be a real number. For every real value of y, y minus 1, which is actually equal to x, must be a real number. So this thing is showing what? That for every element in the codomain of the function, there is some element in the set A with which that element of the set B as the codomain is associated. Means not a single element in the codomain B of the function fx is left for which we are not getting any pre-image in the domain of the function. So that's why this function is of course a surjective function. Here this symbol stands for there exists and this symbol stands for all. Now consider example number 6. Suppose we have a function f defined from n to n, defined as fn is equal to n plus 1 divided by 2 when n is odd, and n by 2 if n is equal to even. Remember that this is known as discrete function. This function is known as discrete function or piecewise function or a split up function. You know well. Now randomly we are going to take an element m of the codomain of this function, and we are going to assume that this is equal to n plus 1 divided by 2. There is no harm to assume this thing. So this will imply n is equal to, we have performed a cross multiplication so that we are getting the value of n as twice m minus 1. Now this twice m minus 1 will always be an odd number for all the member m of this set of natural numbers. This thing is very obvious that for every value of m as a natural number, twice m minus 1 must be an odd number. So this thing is obvious. Again, it will assume that m is equal to fn is equal to n by 2, this thing. Then n is equal to twice m. And this twice m will always be an even number for all m belonging to this set of natural numbers. Even this thing is obvious. Therefore, n belonging to these odd numbers union an even number or even numbers. So if we will unite the set of all the odd numbers and the set of all the even numbers, then we can obtain here the set of natural numbers. And this set of natural numbers is obviously the domain of the function f. So here this calculation is showing what? That for all m belonging to capital N as a codomain of the function, there exists n belonging to capital N. Here this thing is remarkable that this capital N is domain of the function such that m is equal to fn. So this statement holds in the case of this example. So that's why the function f from n to n must be surjective or onto function. Now let us consider the another type, bijectivity of the function or one-one onto functions. Even its definition is mentioned in the study material, but for the sake of your reference right at this time, I am telling you precisely that those functions are called bijective function if it will be both 1 1 and onto, or if it will be both injective and surjective. So here let us understand this situation with the help of example. Suppose we have a function f from a to b defined fx is equal to x plus 1, where a is equal to the set containing elements 1, 2, 3 and b is equal to set containing 2, 3 and 4. So before you people already observed that this function is both injective and surjective, then obviously this function will be a bijective function. Here this thing is obvious that for x1 not equal to x2, this stands for any two distinct elements in the domain of the function, it implies and implied by fx1 is not equal to fx2. Means for distinct elements in the set A, there are distinct images in the set B under this function f. For all x1, x2 belong to capital A as the domain of this function. Therefore, this function f from A to B is injective or 1, 1. Again, since here range of the function f that is equal to the set containing elements 2, 3, 4 and this is equal to b, which is the codomain of the function. So that's why this function is surjective. So since this function is both injective and surjective, that's why this function is bijective or 1, 1 onto function. Consider the next example 2. Suppose we have a function f from R to R, where R is a set of real numbers, define fx is equal to x plus 1. Then this function is obviously bijective function. It is so because that we have already seen before in this video itself that how this function is both injective and surjective. So since this function is both injective and surjective, obviously this function will be a bijective function. Now consider example number 3. Suppose we have a function f defined from the set w to w, where w is the set of whole numbers, defined as fn is equal to n plus 1, where n is equal to even, and n minus 1 when n is equal to odd. Obviously, this is a piecewise function or a split-up function or discrete function. Now let us investigate about the injectivity of this function. Now here there may arise number of cases. In case 1, we are going to assume or take any two elements arbitrarily n1 and n2 from the set W of the domain of this function, and these two elements are even numbers. So let n1 and n2 belong to capital W, which are even such that fn1 is equal to fn2. There is no harm to assume those things that these images are equal to each other. Now, as per the definition of this function, we will have n1 plus 1 equal to n2 plus 1, and this will give us n1 is equal to n2. So in this case, though it is clear that it is injective, but still we must have to consider rest of the cases. In case second, we are going to assume that n1, n2 are odd numbers, where both n1 and n2 are whole numbers. So this n1 and n2 are the two arbitrary odd numbers such that fn1 is equal to fn2. So even in this case, we are getting that n1 is equal to n2. Now consider case third. In this case, we are going to assume that n1 is even but n2 is odd. Then obviously n1 will not be equal to n2, where n1 and n2 are whole numbers. If n1 is even, then fn1 is equal to n1 plus 1. So since n1 is even, then n1 plus 1 must be odd number. So fn1 is equal to an odd number. You will consider n2 as an odd number. Then fn2 means f image of n2, that will be equal to n2 minus 1. So since n2 is odd, then n2 minus 1 must be even number. So now we are observing what? That for n1 not equal to n2, we are getting fn1 not equal to fn2. Means n1 not equal to n2 implies fn1 not equal to fn2. So even this thing is showing what? That our function fx is or fn is injective function. Now consider case 4. In this case, we are observing that n1, we have assumed that n1 is odd number and n2 is an even number. Obviously, even in this case, n1 is not equal to n2. So under this condition, we are getting what? That fn1 is also not equal to fn2. So by observing all the above four cases, we are observing what? That our f from W to W is injective or 1, 1 function. So let us assume that this result is first number result. Now for the investigation of surjectivity of this function, we are going to assume an element m of the set of whole numbers as the codomain of the function. There exists an element n belonging to capital W as the domain of the function such that m is equal to fn is equal to n plus 1. So if this thing will happen, then n is equal to m minus 1. Now this m minus 1 will be an even number for all m is equal to odd number. So if we will assume that m is an odd number, then obviously m minus 1 will be an even number. So we are framing these elements in the frame of even numbers or odd numbers. It is so because that we are considering here the set of whole numbers, and set of whole numbers will contain even numbers and odd numbers both. Even here 0 can be considered as the even number. So if n will be equal to m minus 1, and this will be even number for all m is equal to odd number belonging to capital W. You will take m is equal to fn, and that is equal to n minus 1, because we know that here there are the two different definitions of the function fn. Here the expression of fn is n plus 1 also, and the expression of fn is n minus 1 also. So one time we are taken fn is equal to n plus 1, now we are taking fn is equal to n minus 1. So obviously here n is equal to n plus 1. Before we had taken already even number, now we are going to assume that suppose it is odd number. Then if this will be odd number, then obviously m will be an even number. So this expression will be an odd number for all even values of m. Means to say that if for all even numbers m belong to capital W, our n is equal to m plus 1 must be an odd number. And this thing is quite obvious. So we are observing that m is belonging to the set of all the odd numbers, what we are observing here, union the set of all the even numbers at this place. So if both of these two sets will be united to each other, then we can obtain the set like this: m belonging to the set containing odd numbers union the set containing even numbers. If both of them will be united to each other, then we can get here the set of whole numbers W. So here m is actually the member of codomain of this function. So here this W is actually the codomain of this function. So randomly we had taken one member of codomain of the function with respect to which we were getting an element n in the domain of the function. So this thing is showing what? That our function fn is surjective. Means that here this statement holds that for all m belonging to capital W is equal to codomain of f, there exists small n belonging to capital W is equal to domain of f such that small m is equal to fn. So therefore f from W to W is surjective or onto function. This is result number 2nd. So combining first and second number results, it is obvious that this function is both injective and surjective, so that this function is bijective. So now this was the explanation of the types of functions. In the next video, I will present the concept of composition of functions, and next to next video, I will present the concept of invertible functions and its inverse. Thank you.